Now it's time to speak about the special feature of the new liquid cooling model. And this feature is boiling. There are two different kinds of boiling. Normal, when steam is produced in the engine water jacket, and bulk boiling, as the system is depressurized and the overall coolant temperature in the system becomes higher than the boiling temperature for the ambient pressure. In this case, most of the coolant starts to boil simultaneously, and the boiling will stop as the system pressure becomes equal to ambient. And it's the same as the temperature of the system becomes equal to boiling temperature for the ambient pressure. As I have neither spare Merlin to shoot at nor a 20mm cannon to shoot, I will use a pressure kettle to model bulk boiling. There's a good opportunity to conduct a qualitative test comparing the experiment to the model we use in DCS. First of all, we need to find the area of the nozzle using a cone and a caliper to find the exact pressure and thus initial system temperature, and to use it as a parameter for the model. The diameter is 3.5 mm. And the weight is 74 grams, that gives the kettle absolute pressure about 177 kilopascals. The first test will simulate the case when the hole is above the tank coolant surface, and we can expect good separation of water and steam. So, though the kettle can contain 4 liters, we are pouring only 3 liters of water to leave enough space for steam separation. The heat of water vaporization is very high compared to the heat capacity, so calculations show that only about 80 grams of evaporated water is necessary to cool down this kettle to 100 degrees centigrade. But it requires ideal separation of water. In our case, the steam will contain particles of liquid water as a fog, and it's possible to estimate the average density of this mix, measuring the final quantity of water in the kettle. After the pan is tightly closed, it can be heated. The summer kitchen is dark and mysterious, and now we see how a normal pressurized system will boil. A safety valve opens and steam water mix is spitting out. Now it's time to open the nozzle. Never did it before, so safety is the first. Nothing dangerous really. It's boiling, reducing temperature and pressure quite slowly, exactly as we expected after calculations. The fog plume is not dense, so we can expect not so much water in the stream. The main reason these experiments were started is to prove that the bulk boiling can be much longer than 3 seconds puff somebody expects as a single bullet punctures the tank or radiator. So, as we can see, nothing catastrophic. It boils gradually, reducing temperature and pressure, as it was predicted by the model. Looking ahead, we can show the results the simulation of the process gave. The only one unknown parameter for it was the average density of the stream mixture, and it was set to get the same final quantity of water. So we can expect the overall boiling time in our test to be about 70 seconds. Surely it will not be exactly the same, due to some simplification. For example, the model uses constant mixture density, though in the real test it must vary for the start and the end of boiling. As we can see, the boiling stopped after at least 100 seconds. Anyway, it's a good result, taking into account that outflow of a vapor-liquid two-phase mixture from a nozzle is a very complicated process and requires a lot of time-dependent parameters to be known for more or less accurate modeling. And besides, the holes from the bullets and kettle pipe nozzle are not the same. The more important test we are conducting now is to find a difference, as we have a hole under the liquid surface. In this case, the whole bulk of the liquid instantly becomes a two-phase foam, forming a stream of two-phase mixture as in the first test, but with higher density. Measuring the remaining volume of water after our tests allows to set the average density for the simulation. By the way, the estimated density that we used in DCS simulation turned out to be quite close to what we got in the experiment. So, the difference between experiment and simulation in the first test is about 40%, 30% in the second test. But it will be interesting to compare the ratio between boiling time in different conditions for the experiment and our simulation. And this ratio differs by 10%, which is quite good for this qualitative test.